I'm just checking now. I'm waiting for it to load back in. It's just finishing your intro card, but there's sound on it.
Yeah. Can't hear Rich talking.
Yep. Nope, no audio coming through.
The intro came through.
Yeah.
Yeah, it's working. I can hear myself on the stream.
Okay, right.
The intro came through, and then I heard me. I can hear myself again.
Rich, speak something so we can hear your audio too.
Yeah, I can. 1 second. Right, how's that?
Hear myself again.
Everybody hear me now?
Just a minute, folks. We'll be right with you.
Yeah, we don't have Rich's audio.
That's weird because. How about now? Testing now? Can chat let me know if they can hear me?
Yeah, let's start now. It's all okay.
Okay, brilliant. Right. Fourth time's the charm. Welcome to Becoming Multiplanetary. Sorry for the late start today. We've had some real big issues with audio. We're trying something new. It looks great. It's just a lot of teething problems here. So I'm RichLB, co-host of Becoming Multiplanetary, and we're going to introduce the other hosts, and then we're going to go with our very special guest. So Kage, would you like to lead first?
Yep. Hi, everyone. I am Kage, one of the co-hosts of Becoming Multiplanetary here on the Total Space Network. Thank you for joining us. And with us today, we have...
I'm Mikko, the host of Deep Dive Fridays, and we also have Graham. Take it away.
Yeah, hi everyone. I'm Graham, also known online as the Cosmobiologist or the Professor of Everything Groovy. I love the word groovy, trying to bring it back. I'm a geochemist and mineralogist in training. My work focused on how we look for signs of life and how we study life's interaction with the environment in the polar regions of our planet, but also how we look for life elsewhere. And I think for me, I've always been kind of just wanting to know, are we alone? You know, wanting to be part of that larger question of what it means to be human here on Earth, and to wonder the bigger questions about what it means to be human in this cosmos.
Awesome. Thank you for joining us. And also, I just checked on the stream, and it looks like all of our audio is coming through, so we're good. Yay!
Awesome.
Excellent.
So, Graham, Dr. Lau, where, just before we begin, where are some of the places that our listeners can find you on social media, on your websites, and so forth?
Yeah, my primary website is cosmobiota.com. I coined that term to mean the living matter of the universe. So you can find me there. You can also find me on Twitter and Instagram at Cosmobiologist, and on Facebook and LinkedIn at Astrobiologist.
Great. Thank you for joining us. Happy to have you here.
It's a pleasure to join.
Yeah, cool. So yeah, as was mentioned earlier, today we are going to be talking about the Perseverance Rover, its payload, its payloads, I guess, and also its instruments and its primary mission. So for those who have, I suppose, been maybe a bit under a rock when it comes to space news, in just a few days from now, actually, about 4 days from now, the Perseverance rover and its payloads will be entering the atmosphere of Mars and will go through a period known as the 7 minutes of terror as they go through the atmosphere, deploy the parachute, drop the heat shield, and then the most interesting part of this, use a powered descent using a rocket powered sky crane to find a landing location, lower the Perseverance rover. The sky crane then flies away, and the Perseverance rover begins its mission. Um, yeah, so the first time that they did this was actually with the Curiosity rover. As a matter of fact, the Curiosity rover and Perseverance rover are a lot more similar than they are dissimilar. They have different payloads or different instruments and so forth, but the overall design of them is largely the same, just with improvements that were made over time from the lessons that they learned with the Curiosity rover. But Curiosity also uses sky crane. Um, also is practically the same, at least in the rough dimensions and so forth, and the general function of how the rover works, both Curiosity and Perseverance. I think Perseverance is a bit heavier, though, isn't it?
Slightly, yeah.
Yeah. So,
But it makes sense too to copy a lot, to use the same chassis and to follow the same design for the power source, because you save a lot of money that way.
yeah,
Mm.
right, exactly. I mean, why reinvent the wheel when you already have something that was super successful the first time and still is successful today? So yeah, let me move my screen over a little bit. There we go. Yeah, so let's quickly talk about Perseverance, just to get that out of the way. So Perseverance is about 2,260 pounds or 1,025 kilograms on Earth, whereas on Mars it will be about 866 pounds or 393 kilograms, since Mars is uh, it's a little over one third Earth's gravity. I think it's about like one fourth or something, a little bit between there, like 1.35 or
I
0.35.
think 36 or 40%,
Yeah,
something like
something
that.
like that. Yeah, so it's just a little bit lighter on surface of Mars. Not including the arm, Perseverance is about 10 feet long, 9 feet wide, and 7 feet tall, or in metric, about 3 meters long, 2.7 meters wide, and 2.2 meters tall. And the robotic arm is about 7 feet or 2.1 meters long. Um, Included on the Perseverance rover, there are several different payload instruments, which weigh about 130 pounds or 59 kilograms. 7 instruments in total, which are the MASTCAM Z, Mars Environment Dynamics Analyzer, or MEDA, Mars Oxygen In Situ Resource Utilization Experiment, MOXIE, Planetary Instrument for X-ray Lithochemistry, PIXL, Radar Imager for Mars Subsurface Experiment, RIMFAX, scanning habitable environments with Raman and luminescence for organics and chemicals, Sherlock, and SuperCam. But that actually skips over one particularly interesting instrument, and that is the Ingenuity Drone, which has um, some of its own instruments. I have to like release push to talk so I can scroll. So the Ingenuity drone, and this is for me personally the most interesting part of the Perseverance rover. Um, Not only the search for historical potential life on Mars, but the fact that they're going to do something uh, even uh, also just as revolutionary as looking for life on Mars, and that is they're going to try and fly a mini helicopter drone on the surface of Mars, which is particularly fascinating considering that atmospheric pressure on Mars is only on the surface is only about 1% of what you would find on the surface of Earth. So very, very little material for those blades to chew through. And even still, they're going to try and fly a drone, which is about 4 pounds or 1.8 kilograms on Earth, or 1.5 pounds or 0.68 kilograms on Mars. It's not very big. It's only 1.6 feet or 0.49 meters tall. And the fuselage is actually quite small. The body of the drone is 5.4 inches by 7.7 inches by 6.4 inches, or 13.6 centimeters by 19.5 centimeters by 16.3 centimeters. So not very big. It'll practically fit in your hand, just a little bit bigger than that. And the rotors are 4 feet long or 1.2 meters long. And in order to chew through that very, very thin atmospheric pressure, they'll spin at roughly 2,400 RPM. And the goal there with the Ingenuity drone is to see, can they actually fly something like a rotocopter through the Mars atmosphere. And this is actually one of the particular reasons why they use a rocket powered crane to lower the Perseverance rover, because parachutes just don't really work in Mars. There's not much for them to grab onto. And on Earth, we have a pretty thick atmosphere. There's plenty of material for them to catch onto and slow a vehicle's descent. Just doesn't work on Mars. So that's why they do use a parachute, but it acts more like a drogue chute, if anything else, just to slow the descent a little bit. And then they have to use a rocket powered sky crane in order to lower the payload and instruments, because that's the only way really to the surface of Mars. Yeah. So a lot of information there to digest, but let's go ahead and backpedal a little bit and talk about the scientific mission. So there are 4 parts to the scientific mission with the Perseverance rover, and there are actually 4 key science goals. First, determine if Mars ever supported life. Second, understand the processes and history of climate on Mars. Third, understand the origin and evolution of Mars as a geologic system. And 4, prepare us for human exploration, actually becoming a multiplanetary species. So let's actually talk about that first one. The primary objective, the biggest, most primary objective of the Perseverance rover is to explore an astrobiologically relevant ancient environment on Mars to decipher its geological processes and history, including the assessment of past habitability. So they will be doing this by landing at the Jezero crater, which is just slightly north of the equator of Mars. And it was chosen as a particularly good candidate because, and let me scroll up a little bit. It was chosen as a particularly good candidate on the 4th landing site workshop on October 16th to 18th, 2019, because it appears to have a dried up lake at the bottom of a river delta, which probably dried up about 3.5 billion years ago, but could have great potential for life on Mars. NASA's Odyssey orbiter showed a lot of indications that this could be a really good place to explore. And maybe let's go ahead and pause here and talk about that. Graham, you are the resident cosmobiologist. So, what are your thoughts on this?
Yeah, it's a cool landing site. I think a lot of us in the community in general are just super excited for Jezero. There are other sites across Mars that are really interesting, and as you mentioned, like we have landing site workshops where scientists come together. We have a few proposals for really good landing sites, and then the community decides where the best place is to go, along with all of the engineers who can tell us if we can actually go someplace or not. And with Jezero, you're right. So in this Noachian age, long ago on Mars, named after Noah and the biblical idea of the flood, there was a lot of water activity on Mars. Well, it looks like maybe rivers flowed. They might have even been a sea or an ocean in the northern hemisphere. And so with Jezero, we have this area where at least one time, if not several times, there was a lake filling this crater. And when you look at the pictures, it's so cool because you can see on one side of the crater, you can see where what looks like a river flowed into the crater. And when it met this larger standing body of water, it created a large delta. And so material was flowing from Mars down through this river, coming out and meeting that lake and then dropping material down. And here on Earth, that's a really cool place to look for signs of life, for past activity of life, because materials flowing in that river can then get buried in that delta. And the delta itself could be a very good place for encapsulating the old Martian life if it was there. There's also another site on the other side of the crater where water was appeared to be flowing out of the crater. And so that's also a really good indicator that water was standing inside of this crater as a lake. And there might have been several periods of this lake coming and going through Martian history. And so that makes it a really cool place to look for signs of life. There's some awesome geology in general in the crater to explore. There's going to be clays for us to look at. A lot of really interesting carbonate rocks, rocks that have a carbon and oxygen together inside of them, that are also really, really good at on Earth for preserving signs of ancient life. And so Jezero is a pretty sweet site.
Absolutely. I got a couple of comments that my audio was a little bit quiet. Is it a little bit better?
I think it's better.
Okay.
It sounds okay to me.
All right, cool. Yeah, so let's actually let's talk a little bit about how Perseverance is going to do these explorations for past life on Mars. So, Graham, could you walk us through a little bit about the instrumentation that they're going to use for this, and what kind of methods will they use to find indications of past life?
Absolutely. So, there's so many cool instruments on this rover, and they're not some of the instruments are really about other things besides looking for life. Moxie is an in situ resource utilization test, and we have Ingenuity, which is really cool. The engineer from JPL who's going to fly Ingenuity gave a talk last night at the Planetary Society's Planet Fest, and it was just so cool hearing about what this thing is going to do. I hope we get all 5 flights, if not even more. But if we even get just 1 flight, that's cool. But yeah, one of the primary reasons to send Percy to Mars is to look for signs of ancient or maybe even extant life on Mars. And so some of the instruments that are really good for doing that are things like Pixel, things like SuperCam, which, honestly, if you went back to like 1950 and told people that we'd be driving a rover that's heavier than a car or a small car on Mars, and it would have lasers in its cameras that would shoot the rocks from far away, and it would tell us about the chemistry inside of those rocks, people would laugh you out of the room. And that's so cool. But I have to admit that for me, the instrument that I'm most excited for is Sherlock. I think getting a Raman spectrometer that can do Raman as well as fluorescent spectroscopy on Mars is a huge advancement. And for those watching, this is the first time we'll have Raman on Mars. Raman is very similar to infrared spectroscopy. It's a similar kind of methodology, but the science is a little bit different. And this one we will actually be using a UV light, to then look at the chemistry of the rocks in the surface around where Perseverance is driving. And with this UV Raman spectroscopy, we can actually look for organics too, and learn a bit about the organics. And so if there is life, or if there was life in some of these rocks in that delta or in other regions of the crater at Jezero, I'm really excited for Sherlock to have a chance to use its Raman spectroscopy to look at these things, to tell us the mineralogy, and to tell us if there are organics there, what the organics are. And this is a huge step forward for us for Mars.
Not only that with the Sherlock instruments, but I also saw that there are 2 purposes for the microphones that are going to be on Perseverance. One of the things, and this is a really exciting element of Perseverance, is it will not only record its descent and landing on video, but also will have microphones active to record the audio of this. And on SuperCam, one of the they have a microphone on SuperCam, and one of the purposes of it is also to listen for when they use the laser instrumentation and burn bits of rock, to listen for the sounds that it makes, to not only measure from a various electromagnetic wave or infrared wave diagram as to how things are how the rock is evaporating and what kind of materials it's releasing, but also listen for how it sounds and use that as part of the measurement. That's really interesting. I never would have thought that listening to burning rocks would tell you about its components, and who knew?
Yeah. I mean, and also just to hear the Martian winds. I mean, how cool is that going to be? I love meditation, and I think having a meditation track of Martian winds blowing for a while would be just like so groovy, just to sit there and just listen to Mars in the background.
Have you heard that Insight managed to capture some, like, wind sound?
I hadn't heard that actually. That's pretty cool. I'll have to look into the file that they have for that. Insight's, also a groovy mission that's also still happening, right? I think sometimes people forget that like Curiosity's still active, Insight's still active. We have a bunch of orbiters that are still doing cool science, and then obviously we have a whole bunch of dead robots on the surface of Mars too.
We actually got a question in the chat. Suppose Yara is asking, what is the maximum distance this spectroscope instrument can be used on? Does anyone know?
For SuperCam, I'm not quite sure. It's got to be within like 15, 20 meters at most. It's probably much closer than that. For the Raman, for Sherlock, these are samples that we're bringing into the rover. So SuperCam is the only one that's doing this long range spectroscopy, but we can look that up for sure and see what the distance is.
Already ahead of you.
And we will also have links in the show notes for all the things that we're talking about. I have to really give credit to NASA's Jet Propulsion Laboratory for the exhaustive documentation that they have provided about this entire thing. Anything that you could ever want to know about the Perseverance rover, about Ingenuity, about all of it, they have exhaustive documentation, including even detailed documentation about each and every individual instrument, how it works, how it, what kind of things it measures, how it measures those, just more than you could ever want to know about it. So, yeah, great job to the folks at JPL for putting that together. That's really awesome of you guys.
And if I can add to that, I think it's good that people remember that a lot of these instruments, every single instrument that goes on one of these missions, that instrument has its own principal investigator or PI, the person leading it, but each instrument has its own team. There's a huge team of people, and it's not just from JPL. There's people around the world who are working on these instruments. RIMFAX, for instance, has a lot of Norwegian scientists working on it, and people from the ESA. We have people from Spain who've been working on parts of this mission. There's a lot that goes into developing these missions and designing all the instruments. And when you start looking at like the papers when they come out with all the science that we're doing, they usually have like these just huge like co-author lists, and that's because there's so many people involved in making it happen. As much as we like to like point to one really awesome person who's done a great job, I mean, these are really huge teams of people who are coming together to make these things work.
So I have an answer for Sabolch's question. It is 7 meters.
Oh, that's pretty close. Okay.
20 feet or 7 meters. The spectroscope ranges.
Yeah, and circling back to Graham's thoughts, there's actually a Finnish instrument on the rover too. There's the barometer and another for humidity.
Nice. Yeah, I mean, so like it's a huge team of people, right, from around the world. And I think we're seeing that more and more now in the sciences and in every place, not just on our space missions, but on things like gravitational wave observatories and particle colliders and all kinds of things. Like the teams are getting bigger and bigger because you need a lot of people with expertise from around the world working together to make these things happen.
Yeah, absolutely. It's gone are the days where you had a bunch of flyboys that were the names of the missions. Looking at Gemini and Mercury and Apollo, where everyone knows about Neil Armstrong. No one really knows about who were in the behind the scenes working on things. I mean, we do more and more nowadays, but back then, not really. And nowadays, with just groundbreaking missions like this, it really is a enormous team effort. Not just NASA, but as you mentioned, the European Space Agency is also part of this, and even smaller entities that are that have contributed to this. I think the list of contributors of scientists that are working on this that just contributed to Perseverance is in the thousands, and that's just the people that are working on the instrumentation. Then if you take the engineers that have built this, it just grows exponentially. So really amazing job, all of you folks that have been working on this. I'm sure you're all proud of it, and it's going to be really awesome to see this thing go through the 7 minutes of terror and do wheels down. And maybe actually let's talk about that. What the 7 minutes of terror, the timeline, will look like.
Well,
Yeah, it's gonna be
actually,
one of those moments where like a bunch of us watching around the world are trying to like hold our breath basically as long as we can. I'm going to try my best to just be calm and breathe and relax and just try to visualize what this rover is going through, since we can't have anyone standing on the surface of Mars taking a cool video of it. But we have really beautiful graphics created by people at JPL to show us what this should look like.
well, it's perfect you say that, because that's a perfect segue into video time, show and tell. So we've got the landing animations for Percy queued up first. So if we're gonna take a look at the landing animations, and then we'll do a segment where we just talk about that later. So I will shift us over to the video screen with the power of production.
What's the title of the first video that you're showing?
It is. I will pull it up on stream now.
Is that the 7 minutes to Mars video?
It is the NASA Mars 2020 Perseverance Rover landing animations.
Gotcha.
Alright, now let's try this and see how it goes. Nice.
Amazing
Yeah,
video.
it'd be so cool to watch.
Yeah, yeah, really.
That's just fantastic. Credit goes to the NASA Jet Propulsion Laboratory for that video, and for the folks who made that. Amazing job. Uh, the animations are amazing, and the audio. That's one of the crucial things, is that we'll actually be able to hear these things. This will be the first time we'll actually be able to hear all of that and see, did it match up with their prediction of it. Really excited for that. So, let's talk about the timeline of what this is going to look like. So there are a lot of things that will happen in succession with the landing. So there is first what's called the cruise stage separation. So that is all the times here are going to be in Eastern Standard Time. That will be that's 6 hours behind UTC, correct? No, 5 hours behind UTC.
Yeah, 5.
Unless it's in daylight savings, in which case it's 6, but 5 normally, yes.
Yeah. So all these times will be add 5 hours to this to have the UTC time, so that you have whatever time zone that you're in, makes easier conversion. So first, cruise separation stage happens at 3:38 p.m. Eastern. This is actually where it begins the 7 minutes of terror. So this is where the spacecraft carrying the Perseverance Rover and all of its payload, that includes in the first part of that video, and actually maybe if you want to cue through some of this, or scrub through some of this, Rich, as I'm going through the timeline. So that will be the first part where you have the capsule that is entering, that includes the heat shield and the shell that will enter in the atmosphere. So this will be coming in at about 12,500 miles per hour. I don't have that in converted to metrics. I'm sorry. And that's where the thrusters will begin firing in order to steer it towards its landing target point. This is the point in which the capsule, as it's entering, will adjust its attitude and make sure that it has the right kind of entry entry angle, so that it doesn't skip off the atmosphere and it doesn't come in too shallow and burn up entering the atmosphere. Because the Mars atmosphere is very thin, they really have to get this right, because it's very easy to just be a degree or so off and blow the whole thing. So 1 minute after that, at 3:39 Eastern, is going to be the D-spin maneuver. And that's where it will use its thrusters to stop it from spinning as it's going into its orbit. The capsule will go into a slow spin in order to help keep itself stable in its orbit, as well as make sure that it's able to get the proper measurements to ensure that it's within the correct orbital inclination that it needs to be for its entry. So at this point, it will use its thrusters to slow and eventually stop its spin during its entry. At this point, it will be traveling at over 10,500 miles an hour. About 1 minute after, that will be at 3:40 p.m. Eastern Time. A little over 30 seconds after, actually, it will be about 1,900 miles from the landing site on Mars, where it will drop 2 of its 154-pound balance masses, which will create the correct lift-to-drag ratio as it enters the atmosphere about 5 minutes later. It is currently at that point hitting a very, very thin part of Mars's atmosphere, and about 5 minutes after that is when it will really begin hitting the atmosphere, and that's when the heat shield becomes incredibly important to this. About 8 minutes later, at 3:48 p.m. Eastern, is when the Mars entry begins. So now it's just under 400 miles from the landing site at Jezero Crater, and it will start hitting the atmosphere and heat up, and the heat shield becomes important there. That's also where the biggest loss of signal will happen. Prior to that, there will be still some signal coming from the spacecraft, but around 3:48 p.m. Eastern, once it hits the atmosphere and once that plasma starts to build up on the the heat shield, it will disrupt the electronics ability to send anything back to Earth, and that's when everyone in NASA and elsewhere are going to be chewing on their fingernails for about 7 minutes and hoping for telemetry 7 minutes later. At 3:49 p.m. Eastern is where guidance will really begin to kick in, and that is it'll be traveling at about 11,988 miles per hour at that point, using thrusters to help keep itself on course, and it will hit pockets of atmosphere that may be thicker than others, which can bounce it around and put it off target. So this is where it will continue to use the RCS thrusters that you saw in that video that we just played to keep itself oriented in the right direction, so it comes in at exactly the right kind of inclination to hit the Jezero crater landing site. About 1 minute later, just 5 minutes prior to touchdown, the autonomous entry system will correct for any remaining alignment errors, and this is basically where they commit to where they want to aim the spacecraft. At about 2 minutes later, at 3:52 p.m. Eastern, this is where the straighten up and fly right maneuver comes into play. So NASA's term for this next phase, or that's NASA's term for this next phase, where it will slow down. It's now down to about 1,068 miles per hour, and it will eject 6 more of the balance masses, approximately 13 miles from the landing site. Also, about that time is where the parachute will deploy, and a lot will happen over the next 3 minutes. So that parachute, as I mentioned previously, is only really acting as a drogue chute, since there's not a whole lot for it to grab onto. It's just to kind of keep itself stable, since it's now in a more thicker part of the atmosphere. That parachute is about 70 feet in diameter, and it will still be traveling at twice the speed of sound. Although one of the things I'm kind of curious about with this source is that speed of sound on Earth or speed of sound on Mars, because I think given the how thin the atmosphere is on Mars, that means that sound travels slower, right?
It's a good question. I'm not sure myself.
Yeah, I don't remember actually. So, anyway, so yeah, at this point, since the parachute's not enough to slow down Perseverance for a landing, it's still going at about 160 miles per hour at this point. A few seconds later, actually at exactly 3:52 and 39 seconds Eastern, about 20 seconds after the parachute deploys, that's when the heat shield will pop off. And in the video, that's where you saw that it popped off and fell down to the surface of Mars. This will now expose Perseverance to the atmosphere of Mars. And at this point, the camera and the microphones and other instruments will begin recording. This is when they start beaming back information back to Earth. This is when we'll actually begin to really see the landing in progress once they drop that heat shield. Then, just a few seconds later, the terrain relative navigation begins and the landing site selection happens. This is a really cool part. This is actually going to happen while they still have the parachute attached, just for a short period. And eventually, this is where they will then release the Perseverance Rover, and it will begin using the sky crane to orient itself to some point where it finds a decent enough location to lower, and then lower its descent using the rockets, and then lower the sky crane to release the Perseverance Rover to a gentle touchdown on the surface, let go of that, and then fly away. This is actually maybe a good point to pause here and talk about the terrain relative navigation system. I think they use something kind of similar on Curiosity, but this is a much newer system now. And let's talk about that for a moment.
My understanding of the terrain relative navigation is that it effectively takes pictures of the surrounding landscape and compares them to data that it has stored already to known locations, and it tries to find landmarks, etc. Because obviously on Mars there's no GPS, so it's not like you can navigate to a set of GPS coordinates.
Yeah, and it does it all autonomously, right? I mean, it's doing all this on its own. So there's so much that engineers had to code into this thing that it has to do by itself during this period of time, including comparing what it's looking at on the terrain to what we have from orbital pictures. It's just incredible.
It's actually a really good point that you bring up there that since Mars is so far away from the Earth, when it came to um, lunar missions, it would take about 1.5 to 2 point something seconds for signals to go from the Earth to the Moon and back. So it would just be like having a bit of a laggy Skype call or something nowadays to compare it. But with Mars being so far away from Earth, it can take anywhere between 3 minutes and 22 minutes for a signal to reach Earth from Mars, depending on where Mars is and Earth are in relation to each other in their respective orbits. Um, During this mission, it will take about 11 minutes and 22 seconds for a signal to travel from Mars back to Earth at Mission Control. So by the time Mission Control receives a signal that the rover has reached the top of Mars's atmosphere, Perseverance will have already landed or crashed. We won't know for about 11 and a half minutes after that.
It's weird sitting here and like knowing that the period of time that we're waiting through has already passed at Mars, and the mission knows what happens. It's already done, but we're waiting to find out, and that's just part of space. And we're going to see this a lot more too. Building in autonomy, not just in how missions land on places like Mars, but also for sample collection, for actually doing analyses for driving. With Curiosity, they built a whole new system for Curiosity for how the rover can navigate the terrain around itself as it's driving and can stop before it actually would hit something that we didn't realize was going to be an obstacle for it. It can tell us, that there's a problem here where I'm driving. I need to do something different. And so that helps us a lot too, then saving time and building in better commands for the spacecraft when they're driving around.
Right, exactly. And I like that you brought up all the autonomy that has to go into this, because pretty much for the entirety of this mission, they have to make all these systems be able to make their own autonomous decisions. And all NASA can really do is just predict what should be there, set boundaries for if it exceeds this, then do that. If it's under this boundary, then do this, and then tell it to do that, and then wait for upwards of 22 minutes for feedback to see, was it successful or do we need to do it a little bit differently. And that's actually one of the reasons why if you look at previous successful rover missions, why they move so slowly across the surface and will just creep up just a few centimeters and then take a measurement and maybe creep a few more centimeters, that in order to travel just maybe 10 meters distance could take a month. And it's because they have to do so much measurement and calculation and give boundaries for these rovers of what they can or can't do, and if they need to halt if they hit a certain condition, because there's no real-time driving. It's all right, rover, decide for us. Here are your parameters. Stick within them, and if not, then we'll wait for your feedback and then figure it out and try again.
Percy, take the wheel.
Yeah, and exactly. And it's getting better and better. I mean, eventually maybe we'll send a robot to Mars that will just go, maybe even with legs, just walk around, collect data, and then just decide when to send messages back to us.
I think that's actually one of the plans that Boston Dynamics has for the Spot rover. That not the current iteration of Spot, but another iteration that they want to build is something that could actually use that kind of autonomous machine learning and AI that they have built into it, so they could just send that to another planetary body and say, okay, go walk around and just discover things, figure it out, and we'll just wait for the data that you send back.
Don't forget SpaceBit as well in their Asagumo walking rover.
Absolutely. Yeah. We actually just recently here in Total Space did an interview with SpaceBit, and that's going to be really cool. And it's also, I think the fuselage on that is just about the size of the Ingenuity drone that'll be on Perseverance, and that'll be crawling along the surface of the moon.
Cool.
Yeah, and it will be released very soon.
Yeah. Okay, so moving on. At 3:54 p.m. Eastern is when the back shell separation will happen. So this is where the shell, as you saw, where the parachute is connected to it, will release the entire Perseverance rover, its rocket-powered descent crane, and everything. Just pop it out, and it'll just start falling down at terminal velocity to the surface. Just shortly after that, about a few seconds after it releases, is when the engines will fire up. Hopefully, it'll keep it in a stable orientation. And about 45 seconds later, at 3:54 and 45 seconds Eastern Standard Time, this is it. So this is where it's about has 69 feet to descend. Nice. And I'm sorry, I had to. So this is where the rockets will continue the hovering maneuver using that using the onboard system to determine what would be the safest landing spot, the terrain relative navigation system to find where to finally place the rover down. And it says here that in the timeline, just a few seconds after that, it'll be hovering at about less than 2 miles an hour. It says just a few seconds later, like 5 seconds later, it will actually begin lowering the rover, and it'll use 20-foot cables to lower the rover, and then disconnect and fly away. But this is actually one of the things that we were discussing before this stream, and not sure how long actually can the rover can the sky crane hover, and if it sees that there's too much of a rocky terrain, it just kind of shifts over a little bit. How far can it go? How long can it hover? Not sure on that. So
It's something that I couldn't find in the press kits either, so that's definitely a question that we should send the team if we can.
Yeah. So be interesting to know how much fuel capacity it has to search for safe landing sites, but has some amount. It'll end up around 3:54 and 48 seconds p.m. Eastern. The rover will drop from the descent stage by 20-foot cables, and that's using the sky crane. And as the rover separates, as it's being lowered, its wheels will also deploy and be prepared for landing. And then just a few seconds after that, wheels down, the sky crane will detach. Well, the rover will detach its connections to the cables. Sky crane will fly off and go impact some part of the surface, and mission begins.
Speaking of mission begins, we have a question from one of our patrons, Warhawk, for Dr. Lau. It's how will the Perseverance mission data affect your extraterrestrial biology research?
Well, so for myself, I'm not currently doing work with any of the data from Perseverance, so I should say that up front. A lot of my work was more on extreme environments here on Earth, polar environments, and then comparing those to places like Europa and Enceladus. But I also have some research that is relevant to Mars and also relevant to Percy and to Curiosity, where we're looking at iron and sulfur-rich minerals in a valley in the Arctic that very well likely could also occur in certain places on Mars. Mars has a lot of oxidized iron at the surface, hence the red planet, and so that's super important. And like I mentioned, I've done a bunch of Raman spectroscopy as well. But for me, I'm more of just sitting here, just reading about it and loving the data as it's coming in. I have a lot of colleagues in astrobiology though who are involved with Sherlock and with Pixel, who will be part of those papers, analyzing the data, trying to figure out if we found organics, what they are, what they could imply about potential signs of life. And so there's definitely a lot that we'll be doing with the data. in the community of astrobiologists. Plus, it's really important to remember this is also part of a sample return mission or series of missions. And so not only will Percy be doing all this really cool research with Raman spectroscopy and X-ray chemistry and all this really cool stuff, but it will also be collecting samples. And so as we're going along and using all these instruments to analyze the rock and look for signs of life, we'll also be figuring out which pieces of rock, which samples are the best to put into these little tubes, these little sample caches, and then store them together on the surface so that a later mission can come and pick up these samples and then launch them back to Earth. And so this is a multi-mission series of things that have to happen to bring those samples back. But like for myself, I've done research using synchrotrons. These are large particle accelerators where we use the X-rays coming off of these particle accelerators to do really, really important mineralogical chemistry work. And we can't fly a giant synchrotron, a giant particle accelerator. You can't take that to Mars. But if we bring samples back, we can use really high precision instruments like synchrotrons, really awesome microscopes and other things in our laboratories to study these samples. And so the sample return is also really exciting. I mean, and there's so many cool things about this mission. I mean, with helicopters and oxygen experiments, doing chemistry on the surface, and then sending samples back. And so there's just so much that's going to come out of it.
Yeah, for sure.
And actually, I like that you were talking about all of the things that they're going to do to do sample returns and so forth. This actually might be a good point to check out the second video that we have queued up, Mission Overview, NASA's Perseverance Mars Rover.
No worries, I will get that going. 1 second. I'm actually going to have to load it up for myself as well, because one thing I found producing this is when I play the videos, it will play the audio for everybody watching on the stream, and you guys have your own videos, but it won't play it back to me listening. So I just get the video and no sound. So it was the overview, yeah?
Yes. The mission overview, NASA's Perseverance Mars Rover.
Bear with me one moment, I haven't started it yet. Okay, I've got it here for myself now as well, so 1 moment. Okay, it's going to be playing on the stream now.
You know, Mars is the closest place that we can reach with robotic exploration that we think had a really good chance of having ancient life.
The Perseverance rover will land at a location called Jezero Crater. Jezero Crater is a very interesting place. It's a crater that once held a lake.
There are a lot of craters on the surface of Mars that could have once hosted ancient lakes, but not every crater that we think had a lake actually preserves evidence that that lake was there.
It had an inflow channel and it had an outflow channel. That means it was filled, the crater was filled with water.
In Jezero, we have probably one of the most beautifully preserved delta deposits on Mars in that crater.
This is a wonderful place to live for microorganisms, and it is also a wonderful place for those microorganisms to be preserved so that we can find them now so many billions of years later.
There is no other place on Mars that has the unique combination of a lake setting, a beautifully preserved delta, and the diverse mineralogy that we have in Jezero Crater. So it's truly a special landing site.
The major goal of the Perseverance mission is to investigate astrobiology on Mars, and in particular, to address the question of whether life ever existed on Mars. The Perseverance rover starts with a design that's very similar to Curiosity, but we've added to it a whole new set of science instruments. And these science instruments were purposefully selected to help us in the search for biosignatures.
we're going to be taking microphones with us. For the first time, we're going to have that human sense on another planet.
Perseverance carries with her a grand experiment in spacefaring technology, a helicopter, the name of which is now Ingenuity.
One of the major upgrades that Perseverance has from Curiosity is that it's able to self-drive for a distance of up to 200 meters per day. As the rover is driving, it's literally building the map of the road it's driving on Mars.
Scientists for years have told us that to really unlock the secrets of Mars, we have to bring samples from Mars back to Earth.
So what Mars 2020 is going to do is to drill samples, put them in small tubes. We're going to seal it in its own individual tube. We set them on the surface to provide a target for the second 2 missions, which hopefully will get in development in the next several years and could potentially get the samples back to Earth by 2031.
Perseverance is a very, very profound first step in both our understanding of our place in the universe and a stepping stone towards human exploration on Mars.
So one of the things that they said at the tail end of that video is that one of the to-dos with this is having a way to send those samples back. That's not part of this mission profile. They're just collecting the samples and storing the samples, but they have no way yet to return those. What's currently in the works to build that those sample return missions? Graham?
The current idea is a partnership between NASA and the European Space Agency for ESA to have the return craft to launch off the surface of Mars, bring those samples back, and then we have to catch them here at Earth, and then we have to also make sure that when we bring them down to Earth to study, that they're not, somehow contaminating our environment with potential Mars microbes, which a lot of people also worry about. And so there's a lot that goes into it with making this actually happen, getting these samples back from Mars. And a lot of people might wonder, like, why not just send a mission that's one mission that goes to Mars, collects samples, and launches them back? There are a few reasons for that. It is somewhat driven by politics and money. But also scientifically, having a mission like Percy that can do the science at Mars to make sure we get the right samples is super important. Of the 12 people who walked on the moon, only one of them was a geologist. And guess which one got the actual rocks that were really, really valuable for geologists to study? It was the person who knew what was going on, because they had experience. That the other people were trained. People like Eugene Shoemaker and other geologists and scientists, they taught the Apollo astronauts what samples we wanted to get. But at the same time, having that experience was really important. And so with Perseverance, having a trained astrobiologist robot who's actually able to analyze the samples first and pick the right ones to cache is super important, because we wouldn't want to just land anywhere on Mars and just grab whatever rock is closest and launch it back. It'd be really cool, but at the same time, we want to make sure we get the best possible samples we can, which in the long run will actually save us a lot more money, a lot more time in trying to get really good samples back from Mars.
And you mentioned something there about one major concern is not only contamination, like Earth contamination of Mars samples, but Martian contamination of Earth environment. What would be the instruments on Perseverance that would give us a definitive answer that there is actually something of that nature to be concerned about, that there are microbes present, that there is actually something there that could infect life on Earth? What would show us that on Perseverance?
That's a great question, and I don't think we actually could necessarily say that. And so I'll give you a hypothetical. Say with Perseverance, we land here in the coming week, and we start using Sherlock and Pixel and our other instruments to really get an idea of what's going on at Jezero. Say we actually find what could be a sign of life. You're going to have a large, vigorous debate scientifically about that potential detection. We've decided in the community it can't just be just one single measurement. It has to be several different measurements coming together to imply biogenicity, to imply life in a sample. Now, of course, if we saw a Martian turtle or something walking in front of one of the cameras, that would be pretty definitive. But say we find some organic, some microbial sign of life on Mars, it would be really, really hard for us to know how that life might interact with our life. Say there is life on Mars that's extant, living life right now, and maybe it's in Jezero waiting for us to find it. If we share a lineage, if we share a history, then that life could be extremely dangerous for us because it would likely have very similar biomolecules that could interact with ours. It could be something like a virus, for instance. There's a whole new realm of virology called astrovirology. There are people who are wondering, are viruses a natural form of life that occur, these biological machines occurring in other biospheres? If we bring some Martian viruses back in those samples, we need to be very careful in not releasing them because they'd be extremely difficult to measure with any of the instruments that we have right now at Mars, let alone getting them down to Earth where we can actually look at them first and figure out there's something going on there. There's a lot of work to be done. But say we have a different history. Say life originated on Mars separately from life on Earth, then we really don't know what to expect. Maybe that life really can't interact with our life. Maybe enzymes and things like that are entirely different, or maybe that life is really, really good at consuming Earth life. There are so many things that could happen there that we need to be really cautious about. And I think any sci-fi nerds in the audience might remember Andromeda Strain from Michael Crichton. He might have been the first to really propose this idea in a really interesting way of, what happens if we get an alien sample that actually can harm human life. We don't want to contaminate our planet with life that could somehow just bloom and start eating everything that we know. And before you know it, Earth really is taken over by Martians.
Yeah, great. Thank you. It's a little bit scary to think about, but also kind of fascinating because as you mentioned, there wouldn't be anything that would definitively state with the current instrumentation that yes, there is life there and it is alive and it's may or may not be dangerous to life on Earth. That's little bit frightening.
Well, we do know that perchlorates are harmful to biological molecules. We believe that when Curiosity was taking samples, the reason why it was always coming back negative was because the perchlorate was contaminating the sample somehow.
So the perchlorate salts at the surface of Mars are basically like poison for life as we know it. A friend of mine who studies astrobotany, for instance, likes to point out that in the Martian, Mark Watney would be dead because you just can't grow plants and from perchlorate-rich soils and eat them. You're going to end up very sick and die. You'd have to wash the perchlorates out. And there are people right now who are trying to figure out, when we send humans to Mars, how do we actually get the perchlorates from the surface out of the Martian regolith to use that regolith for things like growing plants and stuff like that. But there's an interesting thing there, right? Like, perchlorates are harmful for biological molecules for life as we know it. But maybe there's a Martian biology that loves perchlorates, and maybe right in the near surface somewhere, a few centimeters down, there are creatures that thrive on perchlorate because it's rich in their environment. We really don't know. And so while the perchlorates are part of why they think the Viking landers couldn't have found life is because those perchlorates would break down organic molecules at the surface. Even with that, there's still a lot of interesting chemistry going on with the perchlorates themselves.
But that's also assuming life as we know it, that there could be some kind of life form that maybe thrives on perchlorates. It's hard to say because we only understand life from the single perspective of what can live and survive on Earth. There could be a completely different kind of life form that lives and thrives on Mars. I mean, I've even seen that it's possible that there could be silicon-based life forms that could survive there. That would just be really difficult for us to understand currently. There are some estimations as to how that could look like, but would it actually be something that would have that same kind of sensitivity? Would it be something that could be a danger to us? Would it be something that could even survive or thrive in an Earth atmosphere? There's a lot of really interesting questions here, and
Yeah, you have to remember, like oxygen breathing. There's a good chance if there are some aliens out there, they probably think we're pretty weird for breathing in oxygen. Oxygen is also highly reactive with organic molecules and breaks molecules down and causes all kinds of issues chemically. And yet we breathe in this toxic molecule for a lot of other life forms. And it's because it's a part of our environment. We evolved with it. And life on Earth has really created it. It's driven the oxygen in our atmosphere. And so it's very dependent on the environment. And so a lot of us in astrobiology, we think that we really need to understand how chemistry evolves with the environment, how biology evolves with the environment around it, to figure out what we should expect. And for silicon-based life, it's been something we've talked about a lot. There are some really good review papers out there more recently looking into potential chemistry for silicon-based life forms, but we still don't know if that could actually happen. And if we have a world that has enough carbon present to make carbon-to-carbon bonds and these long molecules with carbon, why would life want to use silicon is the next big question. And so we have a lot that we have to figure out there, if it's even possible.
And you were mentioning something about the means of detecting these things earlier before the recording. We were talking, about the detections of, or the reported detection of signs of life on Venus, and how that actually can be a little bit overhyped, to put it mildly, as to there are things that could indicate the potential of signs of life, but what it actually really indicates may be something entirely different. So maybe let's talk about that for a moment, and what kind of challenges we might face with the interpretation of measurements coming from Perseverance on Mars, how those two might relate.
I have an interesting idea. How about we let Miko tell us how much he remembers from his deep dive with Graham Lau?
Ooh.
Well, I can say we talked about Venus, we talked about Europa and stuff, but I don't remember the exacts.
Well then, Graham?
I don't know if you can hear my son in the background over here. I have a toddler at home who's having a lot of fun right now, and he's being quite loud. But yeah, so there is some signs of life here in the background on my microphone as well. But yeah, so the phosphine issue with Venus, we should back up a little bit, because you saw in the newspapers late September, early October of last year, journalists saying, scientists say phosphine is on Venus, it's a sign of life, and headlines like that, and that's really not what happened. So in the original paper from these researchers, they used two different radio telescopes. One is the James Clerk Maxwell Telescope in Hawaii. The other one is down in South America. It's called ALMA. It's the Atacama Large Millimeter Submillimeter Array. Using these two telescopes, first with James Clerk Maxwell, the researchers found in their spectra of emissions of radio waves from Venus what appeared to be a little dip in the data at a region suggesting that the atmosphere of Venus had a molecule whose bonds were at the right kind of energy to absorb that radiation, to absorb the radio waves at that level. And that's basically how spectroscopy works. We're looking at emissions and absorptions of light in various ways. And so they had a potential finding of this phosphine, and it had been predicted earlier that this could be on Venus as well. It could be used as a biosignature for life on exoplanets. And we've found this molecule, phosphine, which is a phosphorus atom bound to 3 hydrogens. We found this. We've many times found it on Jupiter and on Saturn. But we have really good chemical ideas, a good hypothesis, a working hypothesis for how that phosphine can form in the environments of the atmospheres of Jupiter and Saturn. We don't have any way for it to form on Venus that we know of. But these researchers, they wanted to make sure they had really good data. And so they then got some time on ALMA, a far more high-resolution instrument, a much better instrument for collecting those data. And they saw that same dip in the data. At a region where it could be the bonds between the phosphorus and the hydrogen that are causing this dip in those data. And so it's a really cool finding, and they did the right thing. They took two different instruments to get the same measurement. They analyzed their data a bunch of times, and then they put together this paper. And in the paper, they say, this appears to potentially be phosphine. We don't have a current model for how phosphine can form in the Venusian atmosphere based on our knowledge of the geochemistry of Venus, based on our knowledge of the photochemistry of the Venusian atmosphere, how light from the sun is interacting with the atmosphere. And so what they basically concluded was this could potentially be a sign of life, but we need more data to find out. And I know a bunch of the researchers on that paper. One of them is also a fellow scientist with Blue Marble Space Institute of Science. And I had a chance to chat with him in depth about the finding, and they were very careful to not say, this is life. Instead, they were like, this could be important. Let's go find out. And now what you probably haven't heard, because it's not been as newsworthy, is there's been a continued debate since then. And many other researchers have now been analyzing their data. They've gone back and reanalyzed the data from ALMA and James Clerk Maxwell telescopes. And a very recent paper from the last 2 weeks, which you can read on a preprint in arXiv, basically they weren't able to find that same dip in the data. And another fellow scientist from our institution is also on this paper saying there is no phosphine based on their analysis of the data. And then another paper has recently come out saying that if that dip is real, and it's really there, it is most likely from sulfur dioxide, which is a sulfur atom bound to two oxygens in the atmosphere of Venus. And we know there's lots of sulfur and oxidized sulfurs, especially in the atmosphere of Venus, which we should expect. There should be sulfur dioxide there. And so this debate continues. It's ongoing. And I wouldn't want to say one way or the other if there's phosphine there, but it's really intriguing. If it is there, we need to find out if it's there. And if it is, we need to figure out where it's coming from. And if it is not a sign of life, if there's some weird geochemistry going on with Venus that we just don't know enough about yet, because we really haven't had a lot of landers on Venus, then that's really important because, like I said, phosphine has already been implicated as a potential sign of life for exoplanets. And so it's really, really good to figure out whether or not that's really true, and whether or not if we find phosphine on another world around another star, whether or not that's a sign of life, or if it's a sign of similar processes to Saturn and Jupiter, or if it's something else like what we're seeing with Venus, if it's really there. And so this happens in science, though. You have the headlines come out, they're attention grabbing, but you don't really get the rest of the debate, which is what science really is. Science is, it's not just a single person, it's lots of people working together in these large teams who they have data, they make interpretations from those data, and then other scientists will basically analyze and figure out, are those interpretations correct? Was the data collected appropriately? I mean, there's so many things that go into it. And so the phosphine on Venus thing is going to be an ongoing issue for some time yet.
Oh, great. Thank you. That was a very thorough answer on that. So what do you think might we face similar kinds of challenges with analyzing data on Mars through the Perseverance rover and also through the instruments on Ingenuity? Could we face similar issues with finding a clear answer as to what it is actually detecting and what does that mean?
Absolutely. Well, first off, so Ingenuity really is just a test. It does have some instruments on board, but we got to be careful not getting too carried away with anything Ingenuity is doing. It's really just to show that we can do powered flight on Mars. And like I said, if it only gets one flight and then crashes when it's trying to land the first time, that'd still be really cool to me. But with the instruments we have on board Perseverance and looking for signs of life, we could make an analysis with several of the instruments together on Perseverance, and you would hear people say this could be life. Again, though, the scientists will be very careful, unless, again, we see some Martian creature walking in front of the cameras, and we have like definitive evidence of Marvin the Martian walking by with his death ray. We're going to have to analyze the rock, looking for potential signs of morphology, like the shapes of cells or past organisms, looking at how the materials in the rock were laying down, So the textures of the rock. But we need more than that. There are many things on Earth that form the structures that are similar to cells, and they do it abiotically. They do it without life. You can take a bunch of detergent, mix it into some water, and you can see those things starting to clump together into cell-like structures. The same thing happens with oils when mixed in waters. And so you have to be very, very careful in how you interpret things like shapes and sizes and textures. And so then we'll go to the next step, which is using the Raman spectrometer and doing the mineralogy, looking at the minerals that are present and the various environments in which they were laying down to figure out, should those minerals be there without the presence of life? Do we need life to explain these minerals? Then we can look at the organic molecules we find using these instruments. Can the organics tell us something about potential biogenicity? And so you start having this layering term, where you have a bunch of potential things that by themselves, one single thing wouldn't implicate life, but bringing them all together, you could actually start saying, this appears to be a biosignature. And then, again, the scientists probably still won't have a paper that says, we found life on Mars. It'll probably be, here are the data. It could be life. Let's figure out, if it's not life, what's going on. And that's usually the approach that we take. However, if we do find definitive signs of life with this rover, I mean, it'd be ground shattering. It would change everything for a lot of us to figure out that we're not alone. And then we have to go the next steps of really learning about what this life is.
Do you think we actually could find those definitive signs, other than Marvin the Martian walking in front of the camera? Can we find definitive signs yet? Or do we just not yet have the instrumentation necessary?
I think yes and no. So again, it depends on what we find. If we get lucky and we find that maybe the delta of Jezero, for instance, happened to be an oasis of life on Mars long ago, maybe we'll come upon, just some patch of rocky material that contains an abundance of potential biosignatures for us to look at. That really could allow us to make a determination that we have found life on Mars. But again, we have to be careful. As Carl Sagan once said, extraordinary claims require extraordinary evidence. And for us to say we have found life on Mars, we need to have extraordinary evidence. We need to have the best evidence possible to definitively say this is life. And so while it's possible, I personally don't think you're going to see it happen. I think even if we find really good evidence that could be life, I think what instead you're going to see is you're going to see all of us in the community saying, we need to store those samples in those sample caches. We need those samples back here in our laboratories for our microscopes and particle accelerators and all the different instrumentation we can use. Those are the samples we want to get back here and really start interrogating more thoroughly. And so I don't think you're going to see anyone say, like, this is life on Mars from the scientific community working on the mission. Not that it can't happen, but I don't think it will. But I do think if we bring one of those samples back, we could really do some really cool work on it too. And that's where you might find the definitive, this is Martian life.
Awesome. Thank you. And to borrow one of those words from Carl Sagan, this has been an extraordinary discussion with you. Again, really, really happy to have you here. We've been going for a little bit over an hour. I think maybe this would be a good point to go ahead and wrap the discussion. So for anybody who is listening currently on the live stream, you're more than welcome to submit questions, and I'd be happy to answer them for the next few minutes. Also, for anybody who is currently listening on Discord, which we only really have another space nut currently listening in. But yeah, if anybody has any questions, feel free to submit them. Happy to ask them. Yeah, go ahead.
What do you think the chances are of us finding techno signatures, Graham? Because I know that naturally your field of expertise is more in biosignatures, but I know more and more that techno signatures are being spoken about. What do you think the likelihood of us actually finding techno signatures may be?
Great question, and I love techno signatures. There's currently a seminar series going on from Goddard. If you look up NASA Goddard techno signatures, in your web search, you can find it. Anyone's allowed to tune in. They've been really great meetings. They're usually Wednesday mornings here in the US, and so afternoon. in Europe. And they've been great meetings. We've had a bunch of scientists who are working in this realm of techno signatures. So to briefly explain what they are, for those who don't know, a techno signature is a more advanced form of biosignature that shows signs of industrial or technological activity. And so we humans produce techno signatures. We've been broadcasting radio waves into space for over a century now. We also, we have chemicals that go into our atmosphere because of our industrial activities. A really good example was the large-scale release of chlorofluorocarbons, or CFCs, before a bunch of nations got together and started creating laws to clean up our air, because we noticed those CFCs were degrading our ozone layer. But we produce these industrial molecules that we don't have a good explanation for how they could arise just on their own, in the geology of a planet. And so looking at exoplanets, maybe, with James Webb Space Telescope coming up, maybe we'll get some really cool spectra from one of these exoplanets of its atmosphere that shows an industrial molecule. So some industrial activity going on. Or, with SETI for a long time, we've been listening to radio waves and looking at light and seeing if there's any patterns in the light energy coming from other worlds to see if there are aliens communicating, sending out messages to, so we can hear from them. And then there's also some other more grand ideas. And I'm a huge science fiction nerd. I loved Halo, the idea of like a big ring world in orbit around a star. I love the idea of Dyson spheres, and that really came from good science. Freeman Dyson, when he made this prediction of what we now call Dyson spheres, named after him, he was arguing that instead of just looking in radio waves for alien technology, we should look in infrared. And his argument was, if an alien civilization is advanced enough to build a large spherical shell around their entire star system to absorb all of the light leaving their star to use for energy, and that shell itself should act as a black body. It should be absorbing radiation and re-emitting it in the infrared. And so Dyson basically said, let's use an infrared telescope to see if there's any big spheres of infrared, anywhere out there in our galaxy. And we can do that pretty soon with James Webb. And so maybe we'll find signs of a Dyson sphere. You might have heard of Tabby's star, where we saw what appeared to be occultation of the light coming from the star that we couldn't explain. And at first, some people wondered, could it be like large rings or structures around Tabby's star that were causing this change in the light? We now think that was actually caused by more like cometary dust, a bunch of dust out around the star that was absorbing light at different levels as it left the star. But it's still possible that it could be something technological, and so it's worth looking into. But these techno signatures, this idea that we could find signs of technological activity out there, is really important. We don't know yet if we're alone in the universe or not. We have to admit logically that we could be the only thing. And if that's the case, then we really need to figure out what's going on here with life on Earth, because we almost have an imperative reason then to continue and flourish and to spread life elsewhere, because that makes us very special. But when you start looking at like the number of stars, the number of worlds, the potential places for life to form out there, it starts to feel like we just can't be alone. There has to be something else. And if that's the case, how long have other worlds had life? Should we expect far more advanced civilizations to be out there? And if they are out there, then maybe techno signatures are one of the more important things for us to look for finding signs of life. And so for all of us in astrobiology, techno signatures are a huge growing realm. A lot of people now trying to put their heads into this problem of what to do. If you're interested in learning more, there is a graduate course at Penn State University in Pennsylvania. They have a resource on their website for the class that has a list of all the best research papers through history in this realm of techno signatures. And so I highly recommend checking that out. It's a good place to find all of the old reading, everything from like the 1940s and up of how we're actually looking for signs of alien intelligence out there.
So we've got two questions that I'm just going to go through quickly, and then we will wrap up, because I'm noticing it's now like 1 hour, 27 minutes. So the first question comes from Jade Finch Scene, and it's, are the samples powder or core samples, or both stroke other? The Perseverance has a coring drill, so it entirely depends on what you're coring into. If you core into a stone that has a porous quality, then chances are when you core into it, it's going to come out as a powder into the sample anyway. Whereas some stones are quite hard, you can core into them and retrieve it mostly intact as a core. So it entirely depends what you're drilling into. And the second question is from Susie R, one of our patrons, and also lead of the TSN fan club, our number one fan, very first fan. What can we expect from MOXIE? How are its findings eventually going to scale up to actual oxygen production on Mars, since it will produce in a day about 6 hours worth of oxygen for a human? What I can say on that from right now is it roughly produces about, 10 grams of oxygen per hour? And the idea is that they don't, there's no information in the press kit. What it does say is that in order to support a mission, the MOXIE unit would need to be 200 times larger in terms of the volume it produces. It would need to be about 200 times larger. So, anybody else with anything to add to those two questions?
Just with MOXIE, remember that is a test. It's a very important instrument, but we're not taking MOXIE with the intentions of MOXIE itself being what we use in the future. MOXIE is really just to show that we can do this. We can use electrochemistry to split the carbon dioxide to make oxygen and carbon monoxide on Mars, and that by itself, if it just does it once, I mean that's a cool feat, and it shows that we can do it on Mars. And I've gotten the question a lot, like, why don't we just do that on Earth and just show that we can do it? And the answer is we have. We've done this a bunch. It works on Earth. We can do it in the laboratory, but we want to show that we can do it with the Martian atmosphere in situ on Mars.
Yeah.
Absolutely. There was also one other question from the builders that they asked earlier. Didn't they say that they would have, quote, live imagery, but isn't the plasma blocking the signals? Yes, technically you're right. And also live, assuming also the 11.5-minute delay for the signals to come from Mars to Earth. But the live aspect of it is more going to be that as mission control at NASA gets information back from Perseverance throughout the entire journey of starting to enter the atmosphere until they get to wheels down. As they get that feedback, they will be reporting live to the press, to the world, as to what they are discovering through all this, whether or not it successfully did make it wheels down, or if they lost telemetry and so forth. The audio and video will actually take some time later to receive that, because one thing to bear in mind is that in order to send signals from Mars, I believe they're with Perseverance, what they're actually going to do is beam that up to a relay satellite that's orbiting Mars that will then cache that information and then shoot that back to Earth. I'm not sure if they will be sending signals directly from the surface of Mars. I don't remember whether or not, but regardless, in order to get those signals from Mars to Earth, even though they have made a lot of improvements on the technology for this, the bandwidth rate is still quite small. I think they can only get maybe about, I think they're around like about a megabit per second or so, maybe a little bit more than that. So very, very slow in terms of what you would experience with like your typical broadband internet. And even though that's the amount of data that they can send, there's also a very high error rate that comes with that. So there's a lot of signal interference and so forth, a lot of data that needs to be replayed and replayed so that they can get the final telemetry and so forth. So the video and audio won't exactly be live so much. What will really be live is the reporting of the telemetry that they're receiving, but that video and audio will come probably some days or maybe a couple of weeks later, and it will be absolutely amazing to see. Really amazing. All right. And with that, let me just double check. Any other questions that we have time for?
I think that's us, I think.
Yeah, I think so. So, first and foremost, Dr. Graham Lau, thank you so much for joining us. It has been an absolute pleasure and honor to have you on our show. You are wise about a lot of things when it comes to astrobiology, and I think this was an absolutely fascinating and enlightening discussion to have with you. So thank you so much for joining us. Really appreciate that.
Yeah, thanks for having me. I really appreciate it. It's great talking to all of you.
And thank
Yeah.
you for replying to the tweet as well, because we were struggling yesterday, and we saw your tweet come back. It's like, oh, Graham's replied. Yes, let's go. So
Yeah.
thank you.
And once
Yeah.
more, Graham, how can people find you on the internet? You want to plug your socials and website again?
Yep, absolutely. Yeah, the best way is cosmobiota.com. But if you want to find me on Twitter and Instagram, I'm at Cosmobiologist. On Facebook and LinkedIn, I'm at Astrobiologist. You can also watch my show, Ask an Astrobiologist from NASA Astrobiology. We do a once-a-month live stream where I talk with other astrobiologists about their careers and research. And honestly, if you look up my name, I'm all over the internet now.
Great, thank you so much. All right, folks. So that's about it for us. I am Kage, one of the co-hosts of Becoming Multiplanetary, and also joining me today are.
I'm RichLB, co-host of Becoming Multiplanetary.
I've been Mikko, the host of Deep Dive Fridays.
And just as we come to the end of each episode, you guys know exactly what I'm going to do. The end of every episode, but wait, I have a special scene for this. You might have actually caught a glimpse of it earlier because I accidentally clicked on the scene by accident. But yeah, let's move over to that now. And here we are, the Patreon scene. So, big shout out to our Patreons. We actually just got another one whilst we were doing this stream. Anthony Mann, thank you very much. So, as at the end of every episode, I always take a moment to thank our patrons. You can see their names scrolling on the right hand side. And as I've said, Anthony's name has yet to be added because he's literally so new that I haven't had a chance to change it yet. But so we have Anthony Mann, we have Adrian Moisa, Framrick, Gio Pagliari, Howard Walker, Jishwana Sebastian, Angry Astronaut, Marco, Sammy, also known as Stinger NSW, Susie R, Warhawk, and What About It. Thank you so much for all of your Patreon donations. As you can see, we just keep doing things to improve the show. Where I've worked on doing these overlays for the past few days now. Had Kage help with some of it as well, and hopefully you guys like it. I'm going to be working a little bit more on them over the next coming weeks, and yeah, let me know what you think.
Yeah, absolutely. And if you like what you've been seeing, please make sure to click like and subscribe, and of course leave a comment if you have any feedback you'd like to give to us. If you'd like to join us in our Discord, you can do so by becoming a patron at patreon.com/totalspace. And the funds that we've been using from Patreon, we actually used to make our new website, which you can find at totalspace.net, which has all of our podcasts and also links our podcast to a series of CDNs that we're now using so that you can have those available across many different platforms. So thank you all for joining us. And Dr. Graham Lau, thank you again so much for joining us. Pleasure to have you. Great. And see y'all next time.